Hi everyone. Today we shall be presenting our work UniCoRN, which is a unified controllable image restoration network for WACV 2026, accepted as an oral presentation. I'm Soumitri Chattopadhyay of UC San Diego, and my co-authors are Debabrata Mandal, Guansen Tong, and Praneeth Chakravarthula from UNC Chapel Hill. Before we go into the paper, let's just talk about the highlights, the overview about the work that we deal with. The problem that we have in hand is real-world image restoration, where real-world images typically suffer from multiple simultaneous degradations like blur, haze, noise, low light, and no existing model can robustly handle them in a unified manner. And most methods assume some prior knowledge of what degradation is present in that image. So in the light of this, we propose this approach called UniCoRN, which is a controllable latent diffusion model. And we drive the restoration process using cheap and interpretable low-level visual cues or visual priors, which may be edge maps or color maps or transmission maps, which essentially indicate the structural and the compositional integrity of the given image. And we model this through a novel multi-head controllable network and mixture of experts that adaptively weight and learn different degradations unifiedly. Our contribution also comprises a real-world benchmark for image restoration, which is, we call it meta restore. And this comprises clean images with screen captured through a metalens camera that obtains compound and entangled real-world degradations. And we evaluate our model on this real-world image restoration benchmark, as well as synthetic mixed degradation and single degradation benchmarks as well. And we see that our model surpasses prior state-of-the-arts on several of these tasks. So to quickly introduce to the task, first we had single degradation removal, where there would be an image with some unique form of degradation imparted onto it, like noise, blur, low contrast, low light, haze, etc. And we would be training models to learn how to restore images from these corruptions. And as we can understand, this is not a very real world simulating task, because in real world, we don't have control over precisely what degradation might be present in a given image. Then the community moved towards synthetic mixed degradations, where you try to mix different degradations synthetically into a given clean image, and your model tries to learn how to restore images from this. Once again, this is a step in the right direction, but not quite as strong, because synthetically injecting degradations don't really mimic the real world. The third category, which is of our most interest, is real world or complex degradations, where you typically have no idea about what degradation might be present in a given image. And the job is to model or to learn how to restore multiple coexisting degradations in a unified manner. So one might ask, what is wrong with just sequentially running different degradation restorers step by step and trying to restore each corruption in each step? So we did this pilot experiment where we would take a degraded image and we would try to restore that image using different restoration schemes one by one. So as you can see, we follow two paths, which are permutations of each other in terms of which restoration is done first. And we observe that these restoration steps are compounding artifacts and they're losing finer details after each step, irrespective of what order we follow. And on the other hand, our unified one-step restoration model was able to faithfully recover the high-quality image from the degraded image without any kind of sequential stepwise processing. And this shows the immediate advantage of having a unified model compared to a sequential stepwise restoration model. Now we come to the methodology, and we have primarily three modules to talk about. One is the low-level visual cues that we have just touched in the previous slides, that how can we obtain some integrity preserving structural and compositional priors from a given degraded image. It could be transmission maps, it could be edge maps, it could be colored maps, and it could be some blind restoration estimates that can be used to guide the controllable restoration process. The next module is a multi-head controllable network. So we have specialized heads per degradation, and they're shared through a frozen stable diffusion backbone, which is pretty much the de facto standard for any visual generation task. And third, we also have a mixture of experts fusion, which adaptively weights these all heads and ensures that we can learn to restore images in a unified manner where multiple degradations might be present. And we package this entire thing and train this using a curriculum learning approach, where we start with simple single degradation tasks and then gradually move on to more complex and mixed degradation or real world degradations in the next steps. First, let's talk about this low-level visual cues. So low-level visual cues, as you can see, typically are some low-level estimates of an image, like edge maps. You can have some transmission maps for modeling haze, you could have some color maps to model some low light images, and you could have some noise maps for a noisy image. And for each of these different kinds of degradations which might occur, we can have an initial estimate of that image. We can have an initial estimate where we remove that particular degradation and we try to get this image. And we assume that these intermediate cleaner images have that structural faithfulness, and these can be used to train a model to obtain more refined and cleaner images in the final step. So this is our framework overall. We have this encoding of these visual cues where we have this low level cues and the high level priors, and we have a network to take care of the encoding of these cues, and that passes into your shared multi-hit control module, which mimics a control net inspired architecture. And these features are then fused into the stable diffusion backbone, which is the final generation backbone, through this mixture of expert adapters, so that our model can learn how to adaptively weight different restorations in a unified way. And we also have some additional textual guidance where we have some prompts which encode some sort of like what degradation task that we want to achieve. And we will show in ablations that this, like including or excluding this, doesn't really, harm or benefit or anything. So which makes our model very flexible and generalizable without the knowledge of any prior image restoration, like what is present in the image. So to talk about the architecture, this is the first part where we encode these low-level visual estimates. This is done using this hierarchical encoder where these features are fused at different resolutions, and the main branch comprises the initial image estimates. We have this task stabilizer unit, which job is to ensure that the model can learn these different confounding degradations faithfully and not get confused, because the degradations can occur and can be present in any compositional ratio. So this task stabilizer unit ensures that we are very stable in terms of training. And we have this mixture of expert adapter, which provides this spatial weighting based on tasks and ensures that we learn how to disentangle and weight different restorations in a unified framework. We also talked about this meta-restore benchmark for real-world degradation removal. And since we have talked about this existing data sets that have synthetically blended corruptions, which are not really real-world, in our case, we have this meta-lens cameras, which are prone to simultaneous degradations. And using these, we capture 1200 image pairs with clean images from the diff2k dataset. And the severely degraded meta-lens captures through an LCD display. And these are our paired, clean, and corrupted images that we use. So this signal capture implicitly ends up modeling a lot of degradations because of the sensor. And finally, we have an image which has all sorts of degradations possible in that image, as you can see in this figure. So first we evaluate on this benchmark, which we proposed. So we have both zero-shot and fine-tuned versions of our model. And we can see that in both cases, we are able to outperform existing state-of-the-arts by significant margins on each of these image restoration standard metrics. And we attribute this fact that these existing models are not tuned or not trained well enough to mimic real-world degradation distributions, and they are not incorporated to handle multiple degradations happening in the same space, which is exactly where our model gives us a very good advantage, and it helps us to get much faithful, high-quality restorations. We show this in qualitative examples as well. The first row shows images captured by the meta-lens, while the last row shows you the clean counterparts. And you can see that these corruption artifacts are pretty much regenerated in each of these baselines, dark lip or AirNet, while ours preserve these spatial intricacies and spatial structures in this restoration process. And once again, we attribute this to the low-level visual cues like edge maps and transmission maps and all these different priors which help us to preserve the integrity of the underlying image. We also move on to some synthetic degradation tasks where you have different degradations injected into the clean image and we try to restore them. And here also we see our model has a huge advantage. It is able to surpass all existing priors by significant margins for each of these synthetic tasks. And once again, the same advantages which were applicable for meta restore also applies to this, where you have multiple degradations and the model is able to decode them or deconstruct them in a very faithful manner. Here are some examples for this. We have this blur plus haze input, and we see that how the model is able to preserve the color, preserve the structures, preserve the patterns and everything from the original image. And this is like this example is a personal favorite here, where you see that this blur and noise has completely disintegrated this structural information with its edges and all. And our model was able to recover all of these intricate edges and patterns and colors inside this architecture in a very faithful manner. And we see the same for the above image as well. We also look into some single degradation removal. Now, it's noteworthy that this is not our primary task. Our primary task was to see how we can remove real world or complex degradations, but we nevertheless try to see our model's efficiency and performance in single degradations. And we see that our model does perform pretty well in especially in this low light enhancement and denoising tasks where we obtain state-of-the-art results. And we are second best for dehazing and deblurring results, but the difference is that we have competitor models here which have been optimized for these tasks specifically, while our UniCoRN model is a universal image restoration model, and this is not optimized for each task specifically. So it's a general purpose model. And we show these examples here as well. And like once again, this first row is a personal favorite for me as well, where we have this severely low light input. Hardly these structures are visible, and we see that these prior methods all fail to faithfully recover the lighting conditions, but UniCoRN is able to not only recover the lighting conditions very faithfully, it is also able to even reconstruct the shadow and everything, which I think is pretty cool for our model, and also preserves the structural fine-grainedness for this hazy and this blurry and noisy inputs. And once again, the attribute goes to this low-level estimates, which helped us to preserve these fine-grained details in the first place. We also conduct some ablations on the design choices, like if there is no textual prompt to tell which task to do, then the model is just guessing which degradation is present and it restores them. Now, we don't see a very significant drop between them. So this means that our model is already generalizing to different tasks without any kind of task guidance whatsoever. And we also see that this architectural design for the encoding of these visual priors was a very crucial choice, was a very crucial design choice, and our model greatly benefited from this design choice in the ablations. So to sum up here, we propose this latent diffusion model called UniCoRN that can restore images having multiple coexisting degradations using a mixture of experts, adapter, and multi-head controllable network for controlling the generation process. And UniCoRN recovers without any prior knowledge of what degradations are present, and it is solely guided by this low-level visual priors or visual cues, which preserve the intrinsic properties of this image. And we also introduced this real-world complex degradation removal benchmark called MetaRestore, which has paired clean and severely corrupted images. And we show that through experiments and qualitative results that our method surpasses all of this previous state-of-the-art works and establishes a new benchmark, as well as very faithfully is able to recover the structural and fine-grained details of images which are corrupted. Thank you for listening. And for more details and the paper, feel free to scan this QR code. Thank you.